multiplication. Remember, I screwed up, right? Last time I didn't explain one line. Somehow I was not thinking, I guess, at that time. You will not probably find faculty members saying they screwed up lecture, right? I don't have any problem saying that. Okay? So what we'll do is we'll go deep into that. Today, we'll understand all aspects of the algorithm that I was trying to show you last time. So what we'll do is we will start off with the entire focus of today's lecture is matrix multiplication and nothing else. Okay? So faculty members, please coordinate because I'll go on silent mode here for the next 15-20 minutes while you guys are doing this, and I'll get my tea and all that good stuff. So groups of 2 or 3. Groups of 2 or 3, and then work on this one. Write an algorithm to multiply 2 matrices. Now, but I want you to test your algorithm, meaning you have to trace it, right? So I gave you the 2 matrices down below. I hope I gave them correctly in terms of dimensions. If I didn't, you fix the dimensions, okay? And in the process of doing that, right, you calculate how many multiplications you are doing. Okay? And then write down the resultant matrix. Everyone understands that? Is there anyone who doesn't understand that? Great. So ready, set, go. Groups of 2 and 3. Faculty members, please facilitate. And I want you to write a good algorithm too. So how to multiply matrices. Okay? We'll use this as a basis for the rest of the discussion. Okay? Your time starts now, 15 minutes. 15 to 20 minutes, okay? It should take that much time. By the time you write the algorithm, test it with the data that I gave you. Because in the process of doing the testing, you will fix the algorithm, I'm sure. Okay? And count your multiplications as you're doing it. And then write your result. Okay, I'm monitoring the chat. I will go on a silent mode for the next 10 to 15 minutes. Faculty members, please facilitate. You can turn on your videos, students. For those of you who have not turned on the video, that way I can enjoy watching all of you doing the work while I'm sipping my tea, right?
Speaking US.
Multiplication can be recursively defined, right? When you have a chain of matrices. I'm getting echo. Give me a second. Somebody needed to mute and they did not. Hold on. And it's associative. That's another important. As long as the dimensions match, whether you multiply A1 and A2 followed by A3, or you do A2, A3, and then multiply it with A1, right? So the result is still the same, okay? Okay, and then you can see the complexity of the matrix multiplication. Ultimately, it comes to PQR, right? So we already noted that. Since it's matrix, it's easy to, it's a theta, right? Now let's look at the chain multiplication, right? So what is chain multiplication? Chain multiplication basically means you have A to N matrices. I'm trying to move my chat so that it's not blocking you guys. Okay, and then we want to compute the product. So now we discussed last class, right? There are many ways of computing them, also called parenthesization. Okay, so let's look at that. Okay. So we are looking at A1, A2, A3, and A4. Okay, we want to compute the product of A1, A2, A3, and A4. Okay, now here I did not give the dimensions. Dimensions we are assuming that they are in sync, the right dimensions. Okay, now there are 5 possible ways of computing them. Okay, you can do it like this, meaning you're first multiplying A3 and A4. By the way, the slide deck would be posted in the community, okay, as always. No need to take notes per se unless that allows you to assimilate. Okay, then you do A2. After that, then you multiply with A1. That's one way. What is the second way? You're multiplying A2 and A3 first. Then you're multiplying with A4. Then you're multiplying with A1. If you look at all the combinations and all that, you'll come up with different ways of doing it. Okay. You can actually prove mathematically. I don't know if I put that in the slide or not. If you have that many things, how many ways in which you can do that? There's a formula for that. Okay. I think I showed that formula in the last week's slide deck. But if I have it here, I'll show it. Okay. Now, here is the interesting slide, right? So what we are saying is you have a P by Q matrix, Q by R, and R by S. Okay. The resultant matrix, of course, is a P by S, correct? That's what you will get ultimately, P by S matrix, when you multiply all those 3, correct? Okay, because when you multiply P by Q and Q by R, you will get a P by R. And you are multiplying P by R with R by S, so you get P by S. Okay, so you can do it as AB followed by C, or do BC and then do A times BC. Okay, so you can see here, when you multiply AB, you get PQR. Remember our formula, right? 3 for loops, PQR, you get that many multiplications, correct? So if you take the resultant matrix, what was it? When you multiply AB, you get a P by R, right? So then it becomes PRS, the second one. So you get those 2. If you do it the other way around, you get QRS plus PQS. Does everyone understand those 2 statements? Is there anyone? I'm seeing this wonderful set of girls here in which school here? I don't know which college is it, 205.736.546. Show of hands. Do you understand those 2 lines there? Raise your hands if you understand. I'm looking at a whole bunch of girls there in the classroom. In the front row, there's a girl sitting with glasses on. Right behind her is one with a red chunni. That is the class I'm referring to. Okay. You can raise your hand high. How high can you raise your hand? Excellent. That's how you should raise your hand, okay? Not like this, keeping it close to chest. Raise your hand means raise your hand. Okay, good. Okay, now you can see here, okay, when P equal 5, Q equal 4, it gave dimensions, right? Now you can see the difference. Multiplying it one way gave you 180 multiplications. Multiplying it the other way gave you only 88. Correct? Obviously, the second way is much better, right? That is what is the key to dynamic programming. The trick is to figure out, given a set of matrices, remember I told you matrices happen all over the place in problem statements, right? In the real world, everything is going to be a join in database world, right? Because you have data in different tables and you want to display based on the query that the user has given. If you go to Amazon, for example, let's say, how many of you shop on Amazon? Do you shop on Amazon? Raise your hand if you shop on Amazon. Or Flipkart. I should say Flipkart because in India you do Flipkart, right? Okay. So whenever you're doing search, for example, of items and all that, behind the scenes, you are seeing lots and lots of joining of the tables based on some query. This dynamic programming logic is used in a way to optimize the query. Okay? So, multiplication sequence is important. Okay, again, somebody, whoever has unmuted, please mute yourself. Okay, I have to mute you again. Hold on. When I mute, 100B is 100 by something. Let me see what that is. And C is 5 by 50. So, see that? When you do AB followed by C, okay, you get 5,000 multiplications. When you do DC, so after you're done AB, that results in a resultant matrix, right? And then that is D. D is the result of multiplying A and B, right? And then do DC, so you get total of, and if you do the other way around, when you do BC, you can see 25,000 multiplications. And with the result, and then you do AE, you get 50,000. Okay? So you can see that in one case, 7,500 multiplications, the other one is 75,000 multiplications. Very costly, right? Now, when you come to the industry where you are a programmer and you're writing a piece of code, I can tell you that if you write code, your manager, unless he's a very strict Indian manager, he would not even bother to see how well you have written that, as long as it works. Okay? Okay. Now, so how do we formulate this chain matrix multiplication problem? That is the key question. So sorry about my dogs barking. You probably have seen somebody outside. Give me a second. Okay. So if you are given dimensions, remember we have different dimensions for matrices, right? So you need an abstraction for dimensions. Okay. So the dimensions are listed PO, P1, O means 0, P1 to up to Pn. Okay. Now that they correspond to, this is where I think they make it kind of like a little bit tricky for us, right? Note the dimensions starting from a subscript 0, where the matrix sequence is starting from A1 to AN. Okay? Now, so PI mentioned PI. The reason why I start with 0 is They are just giving I minus 1, right? It's x by y, right? It's the table. So the column is corresponding to the column's suffix or subscript. What do you call it? Yeah, subscript is corresponding to the and the ith matrix. Okay, and the row suffix is corresponding to just one less than that matrix abstraction. Okay, so given the dimensions, given the matrix sequence, we have to determine the multiplication sequence that minimizes the number of multiplications. Okay, so to put it in other terms, what it means is how do you parenthesize the multiplications? Okay, now yeah, this way I was referring to the formula. So you can see exhaustive search, when you do that, it gives you an omega of 4 raised to n over n raised to 3 by 2. Don't even ask me how we came to that number, okay? Some smart aleck did that and I take it, okay? As simple as that. I never generalized it, right? So the formula, somebody has done it and we use it, okay? That's a lot of search time, okay? The trick is how to make it better. That's where we talk about dynamic programming. DP stands for dynamic programming. Okay? Continue. So what do we do? First, we need to determine the structure of an optimal solution, meaning in this case, parenthesization, right? So to do that, we have to decompose the problem into subproblems. Okay. What are the subproblems? We are saying I, J, we have I and J, right? For every pair. Okay, I, J, and both of them are less than n. N is the upper limit, right? We have to determine the multiplication sequence for A, I to J. Okay, that's what you see in the third line there. A, I dot dot J, you're multiplying A1, AI plus 1. You're going all the way up to AJ. And you want to minimize the multiplications. Okay. Now, what is the dimensionality of Aij? Remember, when you have I, the starting one, it's the first dimension is just I minus 1. That's why you see Pi minus 1. Okay. The second dimension is same as the J. Okay. So Aij has a dimension Pi minus 1 times Pj. That is that matrix would have those dimensions. Does everyone understand that statement here? AI dot dot J is a Pi minus 1 times Pj matrix. Do you want me to go over that again? If you don't understand, put it in the chat. We'll go over that again. Okay. So how do we do that? We'll continue with this, right? So when you're introducing this abstractions, right, it takes a little bit of time to understand. Even if you don't understand it, it's okay. It took me a lot of time to understand it too. These kinds of things, it's hard to remember, right? So I went back and spent some time trying to understand it, and I think I understand it well. Okay, so let's look at it. Okay. So what are we doing for any optimal multiplication sequence? Okay. At the last step, you are multiplying two matrices. You understand that? That's pretty easy to understand, right? When you had A1, A2, A3, you said, okay, I'll multiply A2, A3 first. After you do that, what was the last thing that you did? You multiplied A1 and the result of A2, A3. You're always left with two matrices at the end to multiply. Correct? Any questions on that? That's what this is saying here. For any optimal multiplication sequence, at the last step, you're multiplying two matrices. So depending on some parenthesization, you want to generalize it. That's why you're saying, hey, you have one matrix parenthesis, one subset result is AI to K. Meaning, let's say A1, A2, A3. K could be 3. Okay. And then you have the other one, which is from next one onwards, 4. K plus 1 is 4. 4 to, let's say, 6 if you are given a sequence of 6 matrices, right? So you have whatever that k value is, because you don't know what where it broke, right? Where you are forming the parenthesis. Mute yourself, guys. Somebody unmuted. Okay. So let me mute again. Showing here is with k equal to 5, meaning he broke it at 5. So if you see A3, you go up to that. A4, where the k value is 5. So you have A3, A4, A5 in one parenthesis, and A6 would be separate by itself. Okay. Now when you have separate by itself, you can see the notation 6 to 6. See how he has used in that last line to show that notation, the dot dot notation, because it's basically by itself. It's a single one. So you just repeat that number. Got it? He broke it, the A3 to 6, he parenthesized. So A3 to 6 means on the left, it means you have A3, A4, A5, A6, and they're showing pictorially that A3, you can read the parenthesis there, right? And A6 is by itself. Okay. Now, what is this theory here? Okay. So to determine the optimal sequence is broken down into 2 questions. What are the 2 questions that we should ask? How do we decide where to split the chain? Meaning, what is that k value? Right? So once I know the k value, then you will have 2 main things. One is A1 to, or I to k, I starting from 1 less than or equal to some value, right? And then you have from k plus 1 to j. Remember, the entire resultant matrix will going to be I and j at the end, right? So that's why you see start with I and then end with j. Okay. Now, dynamic programming, remember one of the conditions we said is it should be an optimal substructure. What is an optimal substructure? That means the solution to the subproblems themselves must be optimal. Correct? That's how we defined it, right? If you do not have that subproblems which have that optimal substructure, then dynamic programming may not work. Okay, we listed that in the very beginning itself. Okay. So a final optimal solution of Aij involves splitting into Aik and Ak plus 1 to j. Right? That is the final parenthesization step, right? Then Ai to k and Ak plus 1 to j themselves should be optimal. Right? Its proof is very easy, right? By contradiction, proof by contradiction. You assume it is not optimal. That means there must be some other way of getting less number of multiplications, right? Which contradicts what we said. Hey, if it is optimal, then subproblem should be optimal. So using that logic, you know that the optimal substructure property holds true. Okay, in this case. Okay, that's what the next paragraph says, right? If let us say parenthesization of Ai to k was not optimal, that means there is a better way of parenthesizing it, right? And get a cheaper final solution. And that leads to contradiction. Same thing with respect to Ak plus 1 to j. Okay? Okay. Questions, comments until now? How is everyone doing? Still hanging in there? Okay. By the way, if you think everything is a piece of cake, you will understand everything in the class, be my guest. You have to really go back and review the slides, work out on the examples, and then you will appreciate it more. Okay? The classroom is just to give you more like a guidance, saying, hey, these are the kind of things, and then you go out to work, trace it. That's why I emphasize a lot of tracing of the code. We have to have the recursion, right? We have to define that optimal solution. In knapsack also we did the same thing, right? So the way you do that is you introduce a little bit more notation here. Okay, let's try to understand this notation. If I screw up the notation again, we'll revisit it and we'll fix it. Okay. So we introduce the notation Mij. Okay. What does Mij stand for? It's the minimum number of multiplications needed to compute ai to j. Remember the a dot dot j. Don't think of a ij as one element. It is multiplication of matrices with indexes ai to j. I could like think of it as a1, 2, 3, 4, 5 or something like that. Okay. So Mij stands for the number of multiplications required, minimum number of multiplications required to perform ai to j. Okay. So how do you put together in terms of a formula? No need to memorize this formula. I'm showing it to you, but absolutely no need. I hope that you're not asked to write formulas like this in an exam. At least in my classes in Berkeley, I don't ask them to write these things. But here is the formula. Mij equal to, if values are 0, when I equal to j. There is no need to multiply, right? Because there's only one matrix. When I and j are same, that means what? Only one matrix. There's nothing to multiply. So the number of multiplications required is 0. Got it? Okay. Then, in other cases where I is not equal to j, right, you have to take the minimum between some value of k which falls between I and j. Okay. So you're computing the cost of minimum multiplication from I to k plus the cost of minimum number of multiplication from k to 1 to j. Okay. Plus the dimensionalities. Remember the PQR, Pi minus 1, Pk, Pj. Okay. So you take the minimum for all of those things. That's what that is saying. Okay. Don't worry about the proof here unless your syllabus dictates that we have to prove stuff. I didn't see that. Okay. So we know this Mij. Okay, whatever that formula is given there, right? But what is that k? Okay, we don't know what that k is yet. Okay. Now, what could be the values of k? K is j minus I possible values of k. Obviously, right? When you're starting from ai to aj, how many possibilities are there to split the matrix? When you have 5, let's say I is 1 and j is 5, 5 minus 1, 4. So you basically have 4 or 5 ways of figuring out where to put the banana. Okay? And once you compute that one, then you know where to split the problem. That is what this is saying. Okay? Again, this is a little bit of theory. These things are there to just show you that there is theory behind it. But in real life, you don't have to worry too much about it. Okay? Now, how do you compute that? This was the table, remember? The table that I screwed up when I was trying to explain from bottom up. I didn't do a good job of it. Some faculty member helped me out. That is this step here. So you basically compute it from bottom up fashion. We already said that dynamic programming is a bottoms up approach. Okay. So the table would have a two-dimensional 1 to n table, 1 to n table. Okay. Now, rules are Mij is defined only for I less than or equal to j. Remember, I is never greater than j. Okay. And then you have that equation there, right? So to calculate Mij, if you look at the text there, it says we have to evaluate Mik first and Mk plus 1j. That means we already know those two values. Then you calculate Mik. Okay. Now, the way the calculation is done, you can see here the way how the matrix table is built, right? So you fill the table in increasing order of the length of the matrix chain. Increasing order means what? Then you can see that you have this you should look at the values here, right? M12, M13, M23, 34, different permutations and combinations like that, right? You build a table and you go all the way to M1 to N. That means you covered all the matrices. Okay. Again, theory. Okay. Now let's do some realistic stuff here, right? If you look at these matrices, remember, go back to the exercise that I gave you. Remember, most of the exercise I cover in the class. This is what we are doing in the exercise today. Okay. When you have these three matrices, right? How many entries are there in C? Total PR entries are there. That we know. When you multiply P by Q and Q by R, the number of entries in the resultant matrix is PR. Okay. Now, each of those elements, you take Q time to compute, right? You're doing all the addition, multiplication, addition there, right? And there are Q columns, right? So you get P times Q times R. That is how you arrive at that PQR. When I show earlier, I told you from the for loop viewpoint, right? The three for loops nested, P, Q, and R are the indexes. You get PQR. This is another way in plain English terms to tell you how we arrive at the PQR, total computations. Okay. So let me one more time reiterate. You have matrices A1 through AN. Dimensions are P0, P1 to Pn. Okay. And then any AI dimension. Now, important thing to note, it does not perform the actual multiplication. It just figures out the order. Remember, it's not computing each and every cell in all these things. It is just looking at these dimensions and then figuring it out. Okay. I gave you this example earlier, similar example rather. Okay, you know that. Here is a very naive algorithm. One way to parenthesize. If there are n items, there are n minus 1 places where you can put a parenthesis, right? Either the first item or just the second item, all the way up to n minus 1th item. Okay. Now, if you look at the second bullet, what does it say? If you split here 6, you split at 3. So you form one sublist from 1 to 3, right? And other sublist from 4 to 6 or 4, 5. So that's why you say you create two sublists to be parenthesized. One with k items, right? K could be 2, 3, 4, whatever the k is. And the other one would be n minus k, right? So that's what we did, right? If you have 6 and k is 3, you put 3 in one, and 6 minus 3 is 3, that is n minus k. You put them in the other parenthesis. So in the tree, as it's a binary tree, you have a left subtree and a right subtree, right? So that is, and then ultimately the root of the tree would be computed based on the left subtree and the right subtree. And you recursively do that for all the nodes. Okay. Okay. So there's some equations here. I wanted to remove the slide, but I let it be here. So there's some formula you come up with how you can parenthesize n items, and then it gets into some theory called Catalan numbers. Okay, where we'll come to these Catalan numbers when we talk about binary trees, I think. Okay, so when you have a binary tree of n node, how many ways you can, how many binary trees you can create on n nodes? Remember this fact. Somebody wrote a nice research paper and arrived at this number. Okay, guys, you need to mute yourself. Yes, come up with and we use it. Okay, let's do the solutions here, right? how do we solve it, right? Ultimately, you need to write an algorithm for this, right? The beauty is, yeah, concept is good. We know how to do that. But how do you write the algorithm, right? So a couple of things here, right? So again, notation by now should be piece of cake for you. Let A, I to J be the product of matrices, I through J. We know that. Okay. Then it's a Pi minus 1 times Pj matrix. We know the dimensions because we said P0 to Pn are the dimensions. And then if it is Ai, then we always say Pi minus 1. And then the other dimension will correspond to the J. Okay. So you break that entire optimal sequence of multiplication into two parts. That's what this bullet is saying here, right? One is, what is the value of k for which you will split? Okay, and how do you parenthesize the subchains? Once you know what that k is, then a1 to k would be one parenthesis, and the other ak plus 1 to n is another one. Okay, how do you parenthesize and solve it? You do the same thing recursively. Okay, and since you're doing it recursively, it actually also satisfies the principle of optimality that we talked about earlier. Right, the optimal solution, the total optimal solution, the subsolutions of that also would be optimal. If they are not, then the total solution cannot be optimal. So we proved it in a couple of classes ago. Okay. Now, typically what we do is we use this concept called memoization, meaning you store the solutions to the subproblems in a table or an array. Basically, a table is nothing but an array, right? Two-dimensional array. And then recursively, when you're trying to solve problems, you don't need to resolve the problem that have already been solved. You have the value in the table, and then we use them. Remember, I gave you the example of factorial, for example. Right? You don't need to continue to compute the factorial every single time. Once, let's say, you're doing factorial 6. Factorial 6 is 6 times 5 factorial. Right? And 5 factorial is 5 times 4 factorial. So in the chain, you already see that the lower element factorials have already been computed. So they are saved in an array, and then you simply use them. That's what it says there. Okay. So continuing the progress there, again, we are seeing the Mij concept here. It denotes the minimum number of multiplications needed to compute Ai to J. So here we are showing an example where we are saying, hey, I want to know the minimum number of computations for M3 to 7. That is what has been highlighted, right? So you have a chain from 3 to 7. What is the minimum number of computations, right? So in terms of Pi, remember we have the dimensions there, right? What would be the dimensions of A3 to 7? Can somebody put it in the chat in terms of the abstraction that we gave? We are multiplying M3 to 7. The resultant matrix would have what dimensions in terms of the P notation or the Pi notation? Easy, right? It should be Pi minus 1, 2, right? That means it should be P2 to 7, correct? That's how we define there you go, P2 to P7, perfect, you got it. Okay, now, equal to J, the Mij is 0. We reiterated that again. I already covered that earlier. I'm just reiterating that one. If I is less than J, you're splitting that, right? You're splitting that into Aik, and then you're splitting that into Ak plus 1. The Mij, minimum of I less than K less than J, min Ik plus whatever that formula is, right? So when you're filling out the table, this is the formula that you use to fill out the table. Okay? Again, no need to memorize it. Okay? and then fill out the table and see what you get. Okay, let me stop there. I'll mute them. The problem, and then after you, and then what your answer is. Okay, that is the assignment rest of the day, and then into before you come to the next class. Okay, I will post it now. N. Okay, so in the case of A1, A2, A3, you will have P0 to P3. P0, P1, P2, P3 for the three matrices. Yeah, you're basically doing same thing. You got 5 dimensions there, but it's not the A, it is the P dimension. That's what you're referring to. Got it? But you can figure it out. I posted the slides, print out the slides, review them, do this. That is the homework, guys. And post your answers in the community along with the dimensions that you have. Okay, any other questions? Okay, if not, I will sign off. Send me